Hi everyone. Today we have with us Padmapriya from IJ Pune. She is doing her masters at ISC. She'll be walking us through semi-definite programming through an example of tree coloring. So now you can start.
Yeah, thank you for that introduction. And today I'll be talking about semi-definite programming, as Patra mentioned, but I'll be giving a very intuitive picture and not going into the proof per se. So the idea is to just give an introduction and see how this new technique helps in NP hard problem, which is tree coloring. So, just setting the stage, I know everyone over here may be familiar with graph coloring already, but graph coloring and independent set problem goes as defined. So, we are primarily looking at undirected graphs, and the goal over here is to come up with a map such that you map every vertices to one of the color class. We do this such that the edges get two different colors. So basically, the endpoints of the edges should be differently colored. And the task over here is to find the smallest number of colors that can be used to color a graph. Independent set problem and coloring goes hand in hand. That's because if we have a coloring, each of the color class, if I have C coloring, each of the color class is nothing but an independent set. So independent set problem also goes like this, that you have an undirected graph and you have to find the maximum size subset of vertices that has that doesn't have any adjacent vertices. Okay, so but both of these problems are NP hard. So what can we do? One of the way to cope up with NP hardness is by using approximate algorithms. And it turns out that even in approximate scenario, both of these problems are really hard to solve. So what do I mean by hard in approximate scenario? So it's known that given a constant epsilon greater than zero, it is NP hard to even approximate the independent set problem and coloring to within n to the power of 1 minus epsilon approximation ratio. So what do I mean by this is the optimal independent set size divided by what the best known algorithm could give. This value is going to be as large as n to the power of 1 minus epsilon. So that's pretty large. Even if I say your graph has a very big independent set, we can't even retrieve epsilon fraction of it properly. So given this situation, uh, yeah. So given this situation, what what is the best thing that we know so far? So the best known algorithm today computes the independent set and the tree coloring using n to the power of 0.197 colors. So basically, even if I have a graph which is three colorable, I say you that the graph is three colorable, I require these many colors to color it. And to make the situation even worse, it is known to be NP hard to color a three colorable graph using four colors. So, sorry, did we have a question?
No, no, no.
Yeah, okay. Yeah. So given the setup, let's see what can be done. So we are familiar with integer linear programming and we are familiar with integer linear programming formalization for independent set problem. It's like this. We know that integer linear programming is also NP hard to solve, but let's just go with this and see what can be done to take some inspiration from the independent set problem to do something with coloring. So in the case of integer linear programming, we basically need a variable assigned to every vertex such that this variable is taking value either 0 or 1 to indicate whether this vertex belongs to the independent set or not. And our goal is to maximize the number of vertices that are picked in our independent set. So this works like an indicator function, and it is subjected to these constraints. This just means that if I pick one vertex, I don't pick its neighbor. And this over here is nothing but just captures the fact that xi belongs to 0 and 1. I can hear some echo. Is it fine and audible for others too?
Echo as in
Hello?
your voice again.
Yeah, yeah, my voice again. Yeah, from the start it was.
I can kind of hear it too, but it would be. I think it's because Pranit is recording and probably his mic is connected.
Oh, okay. Oh, yeah, I think
Okay.
it's from 10.
Your audio is audible, like I can hear everything.
Okay, cool then. If it's not disturbing to others, then fine. Okay. Yeah. So this is the independent set integer linear programming formalization. Now we try to just borrow the same idea and have a programming formalization for two coloring. Over here we had a variable for every vertex, but here we not just want to have a variable for every vertex, but also for colors. So basically, given a vertex vi, this, say suppose x I c, this refers to ith vertex having cth colors. So just trying to extend this constraint over here, what do we get? So we don't want the neighbors to have the same color, and we are in two coloring case. So if I have a vertex I with color 1, I don't want its neighbor j to have the same color 1. So this is something I want to do for every edge in the graph. Similarly, I don't want them to have color 2. But there is one more additional constraint, that is every vertex should have at least one color. That we can capture like this. If I put this in a vector, I can say I want its norm to be 1. This ensures that at least one of its entry is going to be 1. So this is the setup we have, and if I call this vector xi, then these two will just simplify to this condition xi dot xj is 0. Similarly, the same idea I can extend to k coloring. So I can have k colors, and in general, the graph is having n vertices. It can be up to n colors, and I can say that a vertex should have at least one color, and I can call this vector just xi, and the same condition for every edge which was there follows here too. Xi dot xj, I want it to be 0. This just again says x1 dot x for every color. So this is the setup we are working at. So to make it clear, the k coloring programming formalization which we have goes like this. Xi dot xj should be equal to 0 for every edge, and xi dot xi should be 1, captures the fact that it's going to be unit vector, and xi is in Rn. So this structure over here, which we have just drawn inspiration from independent set problem, is called a vector programming. So this vector program, it's called vector programming for obvious reasons because we are dealing with vectors over here. Let's see what this gives us. So this is what a vector programming has. The keen ones among you might have noticed one thing, that if because these vectors are in Rn and we have n of these, we just want everything to be orthogonal and have norm 1. Just if we consider orthonormal vectors, they are going to satisfy this. So what does this say? First of all, why are we doing all of these? We came all the way to do this. So intuitively, we wanted only the adjacent vertices to be far. So we want adjacent vertices to be far. But what this gave is everything is equally far. So this is something we don't want. So the idea is if I have all the adjacent vertices very far, I'll be able to pick all the closer vectors and call them non-adjacent and club together to get a non-adjacent set, which is an independent set. So to enforce that the adjacent vertices alone are far and non-adjacent vertices don't become like equally far, one thing we can do is instead of making them orthogonal, push these adjacent vertices very, very far as it can get. Because the space is constrained to be Rn, intuitively, when you push these adjacent vertices far, other vertices tend to clump together. So this is an intuitive, very hand-wavy picture. So to enforce that in here, instead of 0, we are replacing this with lambda and minimizing lambda. Why minimize? What is this? This is cos theta, because these are unit vectors, the dot product is cos theta, and the simple thing is, when cos is negative, that's when your angle becomes big. So this is cos theta, that's when your angle becomes big. So we basically want large separation between adjacent vertices. So this is our modified programming. But why did we do all of this? The nice thing is about the structure that emerged out of all of this. So suppose I simply write this xi dot xj as a matrix with ijth entry being this dot product. Then something nice happens. Such matrix, if we notice, can be written as a product of two matrices, where I can just call one as transpose of the other. So this X can be written as product of two matrices. Why is that nice? Such matrices are called positive semi-definite matrices. That brings us into the regime of positive semi-definite programming. So how am I saying this is positive semi-definite matrix? Just to go over the definition to see that everyone is in the same page. A positive semi-definite matrix is denoted like this. It is one that has all non-negative eigenvalues. And there's a characteristic theorem that states that being a positive semi-definite matrix and being able to write the matrix as U transpose U for some matrix U, and having the fact that X transpose AX is always greater than 0, greater than equal to 0 for every vector in Rn, all of these are equivalent definitions. So we were just using the second definition to comment that this matrix was a positive semi-definite matrix. And the nice thing about this is, unlike integer linear programming, this type of semi-definite programming is solvable. We can solve such vector programming, we can solve such semi-definite programming in polytime. So this can be done in polytime. This is a relaxation, another form of relaxation to our integer linear programming, which is different from just the linear programming. So given this, now for two coloring, so we have, if suppose we have two vectors, V and its neighbors, intuitively again, we get the largest separation. So we were talking about this programming here, and we agreed on the fact that lambda captures the cos theta value, and largest separation is what it's achieved here by minimizing lambda. So largest separation between two vectors is going to be 180 degree. Okay, so given this, after I solve my integer linear programming, everything is a unit vector, so I can write it in unit sphere, not sphere. We are in Rn, but for visualization, I'm drawing in a plane. So we'll end up getting a lot of these vectors, and vector and its neighbors will be opposite to each other. Given this, how can I color it? So I'm just drawing all these vectors. So this and this is neighbors, they're 180 degree apart. That's all we know. Given this solution, can one of you suggest how we can color it? Anyone has any idea here? Like some intuitive, some just a guess. So all all you know is the vectors are 180 degree apart if they are neighbors.
So
Okay,
like color
so
them the same.
color, sorry.
Then color the two opposite vectors the same.
So the neighbors are going to be
Oh,
paths.
oh,
So
oh, okay, okay, okay.
yeah, yeah. Okay. So actually, it turns out that you can you can choose any random vector, and plane defined by it. Now, any plane in Rn or in anything will be able to distinguish between 180 degrees. What we can say is every vector in this half has angle lesser than 180. So you're guaranteed that all of these are going to be not adjacent, because adjacent is forced to be 180 by our programming. So every adjacent has this constraint imposed in it. So this can be colored nicely in this way. And we should expect such a thing because 2 coloring is polytime solvable. So here we can nicely just pick any random plane and cut it. So that's why we did all of these work to get nice vectors in Rn and geometrically try to get independent sets. This is an independent set and this is an independent set, and color it come independent set with one color. So is this idea fine and for everyone? Can I proceed? If anyone has a doubt, I think this is a good time before going into 3 coloring. Okay, cool. I can see some thumbs up. That's nice. So now all this hard work we did. So what us before that, I didn't formally show you that this should be 180 degree. I mean, it's very intuitive, but still we have Rn space, and if I give 3 vectors or 2 vectors, and they have to be maximally separated, because we have like not just a plane, probably there is better ways to separate. Probably I can achieve more than 180 degree angles or something like that. So the first question should be how to find this lambda value. So what will be the minimal value? And for this, let's take an example of 3 coloring only. So we have V1, V2, V3, 3 vertices, just a simple triangle. So I have like V1, V2, V3. So I'm simply drawing it intuitively in such a way, but they need not be in 180 degree separation in Rn. So the question is, given 3 unit vectors, what is the farthest apart it can be? In here it's R3, but in general Rn. What is the angle between all of these? So again, I'll just represent the dot products in such a matrix, like how I did for the X matrix before. And we'll call each of these cost values X, Y, Z. Basically, each of these dot product X, Y, Z. Again, we are putting it in this form to just exploit the fact that this is a positive semidefinite matrix. Positive semidefinite matrix. What do we know about this is all of its eigenvalues are positive, like non-negative. So we know their eigenvalues are going to be greater than equal to 0. So we are going to use this to find the angle, what cos theta can be, or what of these x, y, z are. So without loss of generality, because of the symmetry, we have 3 unit vectors in R and none of it is special or anything. So we are free to assume that all of these cos thetas are going to be same value. So I'll just replace all of this with value A. So this is the matrix we get, the determinant matrix, and we are going to find the eigenvalue matrix, and we'll be finding the eigenvalues and eigenvectors from here. And if you compute, you will find that the eigenvalues are 2a plus 1 and 1 minus a. Now we know these should be positive, precisely greater than equal to 0, non-negative. We will get the value of a. A was our xyz, which was our cos thetas, to be minus half. The minimal value a can take is minus half. This is the optimal solution, and this corresponds to 1 cos minus half is nothing but 120 degrees. So the intuition we had was right. The vectors are going to be 120-degree apart in R3 also. And you can convince yourself in bigger matrices also it is going to be same. But how can you do that when you have like K coloring? Then you have an Rn dimension matrix. It's not going to be easy to find eigenvalues in this form. So one nice thing about the form of the matrix M is that if you see how it is, it's basically all A's and just the diagonal has 1. So we are subtracting by minus mu I identity matrix. So we have this minus mu over here, but otherwise M only has like M only has ones in its diagonal. So the form of M is like this, and we can say this matrix over here, depending on the dimension, if it's like n dimensional or K coloring has K dimension, its eigenvalue is going to be Ka, and the corresponding eigenvector is going to be all ones. And for this matrix over here, it's an identity matrix. So its eigenvectors are going to be all our bases, the standard basis of Rn, and so on. And all of this is going to have 1 plus A as its eigenvalue. So together we have Ka plus 1 plus A as one of M's eigenvalue, and all others is 1, sorry, it's minus. This is also minus. So all others are 1 minus A, rest. This is just K minus 1, A plus 1. And to convince ourselves, if we look back, what we got, it's 2. This is nothing but, we knew that the graph is 3 colorable. So it's just 3 minus 1 into A plus 1, and all others will be 1 minus A. Depending on the dimension, you have those many eigenvalues, and all of that correspond to a degenerate subspace. So this is the setup, and with this, you can see that this equation is what corresponds to this. So A will be greater than equal to minus 1 by K minus 1 for a K colorable graph. So notice how this, because the negative value, it's going to decrease, your angle will move closer and closer to 90 degrees as there are more and more colors. And when the graph is like complete graph, when you have to use n colors, you come back to the fact that the only solution is n orthogonal vectors. So this value is going to decrease, as in the theta value corresponding to this. This is cos theta, is going to keep decreasing and approach 90 degrees as K increases. So given all of these setup, now we know for 3 coloring, the angle is going to be 120 degree apart. But it's just that mutually adjacent vertices are going to be 120 degree apart. So if V, W, X, all of these are adjacent to each other, then they are going to be 120 degree apart. So the graph can have so many more vectors, and each of it mutually is going to be 120 degree apart. And we are in a bigger space, so things can be anywhere in Rn. All we know is just mutually 120 degree apart. If we recall what we did in 2 coloring case, things were 180 degree apart. That made it very easy to cut with any random plane. But here, things are a little more tricky. Obviously, we don't expect things to be easy because 3 coloring is NP hard. So in this situation, what is the best we can do? Just by extrapolating, let's first try doing what we did in the case of 2 coloring. If I just take a random plane over here, cut this, we see that so many adjacent vectors are going to fall in the same side. Imagine this whole setup to be our Earth. Yeah, it's Earth now. And cutting through the plane, passing through origin, it's like cutting across equator. So this plane is nothing but Vi,
or xi's here, these vectors, dot r, if the normal of the plane is r, so this is greater than equal to 0 is all we have. But to avoid picking neighbors, I don't want to pick neighbors like this, a lot of neighbors. One thing I can do is cut across in a higher latitude. In the earth, it's like cutting across Tropic of Cancer or closer and closer to the pole. The more closer I go to the pole, I am hardly going to pick vectors. The idea is to pick lesser, so increase the latitude will decrease the number of neighbors picked. And as a con, we are going to decrease the number of vectors itself picked. So I don't want to end up picking like very less vertices. I want to pick a larger vertices. So there is a trade-off between what latitude you would want to fix. This epsilon value gives you a good trade-off. Makes you pick very less neighbors and more vertices, so that the idea at the end is like what we did in two coloring case, pick an independent set, color it off. That's all. That's the simple idea which we are trying to do. So I want to pick an independent set, so I increase this latitude. So this is the overall intuition behind all this semi-definite programming and vector programming setup, where we have associated vectors with every vertex. Now we'll come to the algorithm part. The algorithm is whatever we have seen so far, just putting together everything. First, solve the semi-definite programming SDP setup, and from here, try to get a independent set. So to get the independent set, what we are doing is we are choosing a random unit vector. Yes?
What was that minimize 0? Like in
Oh,
the previous.
yeah, nice that you noticed this. So basically, so while I've been putting lambda over here, right? Minimize lambda. So once you know the value of lambda, we have like actually computed the value of lambda. This is the minimum value of lambda. So instead of that, I could just put the minimize lambda. I'm just replacing the actual value of lambda. Now I have the value of lambda. There is no constraint anymore. I'm sorry, I slipped to mention this fact. There's no constraint anymore. So there is no optimization function anymore. You have nothing to optimize. All you have a constraint. This gives you everything. So just for the semi-definite programming setup, even in linear programming, you do this when you don't have any optimization function. You can put any dummy optimization function over here, because all you want is captured in the constraint itself. So this equivalently, if I really know that the graph is recolorable, I might as well put the value directly. Or I can just put less than equal to lambda, and the program itself will have this lambda is equal to minus half. It will compute. So, well, it solves this. Yeah.
Yes.
So, yeah, that's why we have like minimize 0, because we have no constraint. We have no optimization function. So, coming back to the algorithm, we first solve this SDP, and now the idea is to get an independent set and then color it off. So to get the independent set, we choose a random unit vector, random, but we want each of this entry random as in Gaussian random, which is normally distributed. Why do we want such a thing? When we see the analysis part, if we have time, we can go to the analysis. So when we have the analysis part, picking it Gaussianly helps us to exactly say a lot of things. Like the number of independent sets written, number of vertices written by this algorithm, and number of colors used. So yeah, so we pick a random unit vector, and then we fix the value of epsilon. This epsilon is the latitude I was saying. So in this diagram, this epsilon defines where we are cutting. We don't want to cut it in 0 for the reasons I was mentioning before. And again, this exact value of epsilon, why are we picking that? For 3 coloring, it turns out this number is nice, and by nice, again, you will see it in the analysis. So take my word for 3 coloring, this number is nice, and this capital delta is the maximum degree of the vertex in the graph. So after cutting the plane, so what we are doing is first our linear programming gives all of these vectors which are 120-degree apart everywhere, and I am picking a random unit vector r, and I'm cutting in some higher latitude. This is given by this epsilon, and now everything that falls over here, every vertex I, such that so we have taken xi to be the variable, xi dot r greater than equal to 0, everything that falls here, I'm collecting in a set called S epsilon. This set is not 100% guaranteed to be independent set. All we are doing is, making sure that as much as neighbors as possible are not taken. But this doesn't mean it has 0 neighbors inside it. So what do we do for every edge over here, every edge in the graph? We see whether both the endpoints are in S epsilon. If they are, then we just add it to a set called D. And then you are just removing this D from our S and defining another set, S prime epsilon. This is an independent set by construction. And you are just returning S prime epsilon. So this number over here, we will see later in the analysis, ensures that your S prime epsilon is at least as large as half of your S epsilon. So most of the vertices over here are going to be non-adjacent. So that's pretty much what we want. That's why we are choosing all of this. Now this algorithm just returns an independent set. Now what to do after this? Simple. We are just going to, given an independent set of size some qn, that's going to return some size qn, just color all of these with one color and repeat the process until only one vertex is left, coloring the graph. So this gives an approximate algorithm. You're not certain to get exactly 3 independent sets by this algorithm. There can be more cuts needed to get each big chunk of independent set, leading to more than 3 colors. How many exactly is what this theorem is going to say. So this algorithm returns an independent set of at least this size, omega of n into delta to the power of minus 1 by 3 into ln delta to the power of minus 1 by 2. So again, the proofs are, we can see the proof if the time permits, but if you take my word for this, if you believe in this theorem, we have this big of an independent set, and here we are saying Qn. Yeah.
Padmapriya, I missed something. Delta is the highest degree, right?
Yes. Yeah, okay. Yeah. Delta is the highest degree. So here Qn is what we are denoting. So leaving the n, this is our Q part. Now, this algorithm, how many colors does it use to color? That's the next question. So basically, every time this algorithm is returning qn many vertices. So after one iteration, we have n minus qn many vertices left. So this is like 1 minus q into n. So after k iterations, you'll have 1 minus q to the power of kn vertices left. So it's a fact that 1 minus x is less than equal to e to the power of minus x. This gives us the value of k as this number over here, ln n by q. So I think the minus is a typo. So we would need these many colors, because every iteration I'm coloring with one color, and the next iteration I'm coloring with a new color. So the number of iterations this algorithm runs is k iterations, which is ln n by q. So ln n by q colors is substituting this value from this old theorem. We know q is this number, delta and ln deltas. If we put in this expression, you will end up getting the algorithm uses ln n to the power of 3 by 2 delta 1 by 2 many colors. So again, the proofs will come later if we get time. Initially, I had little difficulties to understand how we are capturing vertices as vectors and then using semi-definite programming. So for my learning, I tried to just program some things and see these things visually happen. So I thought of sharing these visuals with you people too. So I would now again screen share and show you some visuals. Before that, if we have any questions, we can probably get that cleared before going to the visuals. Do we have any questions?
What does the proof, which kind of technique does the proof uses? Like
very simple things. I think we'll have time to see some of the proofs.
okay.
Yeah.
Yes.
So then we'll go to the visuals now. Can you see my screen? Okay, but
Padmapriya, I'm not able to see your screen. What's up, Padmapriya?
yeah, guys, I'm sorry because I was not able to see my screen. I had to rejoin again. Can you people see my screen now? Hello?
I cannot.
Yes.
I can't.
I can see.
Oh.
Yes. Yes, I see some thumbs up, so I think it's fine.
Yeah, now I can see it. Different screen.
Yes. Yeah, okay. So this one over here is the FDP solution of a triangle graph. So if you remember in the finding lambda part, where we found that for three colorable graph, the lambda is minus half, we just use a small example of a triangle graph. So you see how nicely this is giving you exactly a solution in a plane and 120 degrees. The next we'll see is a bipartite graph. This is bipartite, though it doesn't appear nicely bipartite. It's not connected, but bipartite graph. So bipartite graph, it's two colorable, and we know that the vectors are going to be 180 degree apart. So here the numbering is from 0, there the numbering is from 1, bear with me for that. So here this says vertex 2 and vertex 5 are neighbors. Because they are neighbors, they are far apart. So here vertex 2 corresponds to vertex 1 and vertex 5 corresponds to vertex 4 because the numbering is 0. So these are neighbors, so they are far apart over there. And for another example, 0 and 2 is non-neighbors, which means 1 and 3 are non-neighbors. 1 and 3 are exactly superimposed here. I don't know whether it's clear, but
Can you lower your screen a little bit? Like the sphere part, like
oh,
it's
sorry.
up.
Yes.
Now it is. Yes.
Yeah. So yeah, and there if you see 4, 7, and 6, all of them are clumped together, which means they're all non-adjacent. So they're clumped together. Only adjacent is far. So 4 corresponds to everything has to be plus 1 over here. So 5 and what all were together? 4, 7, and 6. So we have 3 and 7 and 6. Okay, I should do a really -1. So everything -1 because of the labeling is off. But the basic idea is you can just see that the adjacent vertices are together and are very far, and non-adjacent are together. So that's this graph, and we will see how the plane cuts. So this plane passes through the origin, and because it's a bipartite graph, I can safely just pick any plane in Rn, cut across the sphere in Rn, and everything to one side is going to be non-adjacent. So this gives a coloring. So anything which has this X mark is in the one side of the plane, and anything that doesn't have this X mark is in the other side of the plane. So that gives us this coloring, which is a valid coloring, if you see. And it's two colored, it's a bipartite graph. And then we are going to see a three coloring example. So this graph is three colorable. What is a graph? It's just a cycle, just an odd cycle. So it's three colorable, we know that. And this is the SDP solution. And this plane I have chosen in some, this is a random value of epsilon, very arbitrary value of epsilon, not the epsilon given by the algorithm. I think I chose like some 0.5 or 0.7. So this cut here, and only one of the vertex is retrieved over here, and that we are coloring with one color. Basically, we'll repeat this process, coloring every single time we get an independent set with one color. So we'll end up coloring this graph with more than three colors. So these are the visuals which I had. Now we can, if you again have to ask anything, you can ask here, and we'll go into the proofs. We'll see as much as possible. Can I move into the proofs? Or do I have any questions?
I think we can move on.
Okay, cool then. Yeah. Yes, is my screen visible?
Yes.
Okay, cool. So to prove these main results, which is this theorem, to say how many vertices are retrieved by our independent set algorithm and how many colors we use to color, we'll first start off with few lemmas. So the first one is the expected size of S epsilon. So we are just randomly choosing a plane and cutting. So how many vertices are we expected to retrieve after this cut? Is the question we have first. Is going to be this number over here. Here, phi is the cumulative distribution function, or whatever it's called, of the Gaussian randomness. So that's if you remember the R which we picked, the vector R, is Gaussianly distributed. What I mean is R1 to Rn constant. It has like n components, and each of these Ri is from a standard normal distribution, mean 0 and standard deviation 1. So this is just a probability density function of a standard normal distribution, and this is what we are claiming. Why? It's because this is also Gaussianly distributed. If we pick any arbitrary Vi, so it has fixed entries in it, and if I multiply it with each Ri, which is Gaussianly distributed, so this is constant times a Gaussian distribution. So overall, this dot product is also going to be Gaussianly distributed. Because this is Gaussianly distributed, I am asking when will this be greater than equal to epsilon? That is when this Vi is picked into S epsilon. So this, by definition of phi, so this is my Gaussian. So by definition of phi, this is going to be just, if there is some epsilon over here, this is the part where it's greater than equal to epsilon. So it's 1 minus this integral from negative infinity to epsilon. So thus, this size is expected to be n times of this. So because each of these components are Gaussian distributed, we have like n many components, and this follows. So is this lemma fine? Given this lemma, we'll go to some facts. So these facts I won't be proving because I thought I won't have time, and this is that you can look up for these things. This fact is the projection of R onto two unit vectors E1 and E2. So I'm talking about projection of R, which is our Gaussianly distributed, into two unit vectors E1 and E2. They can be anywhere. This is independent and normally distributed. It will be normally distributed, we know, but the important fact is independent. Only with mean 0 and variance 1, if and only if these two are orthonormal in this case. So this is some fact that you have to take me for my word. And another fact is, if for any x greater than 0, this is going to be true. Basically, this 1 minus phi of x, where phi is this function, this is going to lie between these two values, x by 1 plus x squared, p of x. P of x is the probability density function of standard normal. So this number is going to lie between these two. This can be just with some two differentiation of this function and just rearrangement, you can prove this. So given these two facts, we'll now go to proving another theorem. So this, first we saw how many vectors your S epsilon is going to retrieve. This we saw is on expectation n into 1 minus phi of x. Now from here I am going to reduce and get a subset S prime epsilon of independent set. Of independent set. What will this size be? So if you remember our algorithm, what it does is it goes over every edge ij and it sees whether I and j together belong to the S. Then it puts this ij into a set D, and it computes its prime epsilon by removing D from our S. So this is how we got. By construction, we saw it's an independent set. But how many vertices will we retrieve? Will it happen that all of these vectors are going away in D and you get 0 for S prime epsilon? Can that happen? Because this is what our algorithm returns at the end. It returns this. So this we will show the probability that I belongs to a vertex I here belongs to S prime epsilon, given that I belongs to S epsilon, is at most this number, delta times phi of root 3 epsilon. So how we will see here. So do we have time to go through this proof? I think fine, right?
How much time it will take? Like 10, 20 minutes, right?
Yeah, 10 minutes. I can run through this proof fast.
No problem.
Yes, cool then. So to prove this, first we should recall that we have this solution from our SPP. So we are talking in 3 coloring setup. Here we know that if you have ij which is adjacent, this is going to be the case. Now what you're doing is we will resolve v of I along v of j along vi and a perpendicular and an orthogonal vector to vi. So basically if you have vi, if you have an u, you are resolving some vj along these two. From this follows, and this is unit vector, so this also follows, and you do some rearrangement, you get this u as this number, 2 by root 3 into this number. Why did we do this? Because recall we have this fact. we want two unit vectors but which are orthogonal. To talk about some independence. So given this, what can we say? Vi dot r is greater than epsilon. Such vectors only are captured in our S epsilon set. Vj dot r is also greater than epsilon because they are adjacent vertices which end up in S epsilon. We want to calculate how many adjacent vertices end up in S epsilon because that's what we are going to delete from this. So that's why we are doing all of this. So this two fact together means this value u, when you take dot product with r, is going to be this number, which is root 3 epsilon. So with all of these things together, because vi and u are orthogonal to each other, we know this is also normally distributed. And this is independent of vi. So given this, we can say that the probability of an edge belonging to S epsilon, what I mean is both these vertices falling in. When will this happen? When both of these vectors satisfy this condition, is going to be equal to probability of Vj times r such that Vi times r, and this condition, this we are looking for every neighbor of j. So every neighbor of j, because at most j can have delta many neighbors, this delta comes. And these two together is going to be standard normal distribution, and that we are taking in these two information with one information u, and this u should be greater than root 3 epsilon for this to happen. So it should be greater than equal to root 3 epsilon. And this is normally distributed, so greater than equal to root 3 will happen with probability 1 minus phi of root 3 epsilon. So 1 minus phi I am representing as phi prime, or we can just say delta 1 minus phi of root 3 epsilon. So that is what we needed. This is also phi prime. Yeah. So we have proved this statement. Now we'll finally come to the proof of the main result. The result of how many vertices are retrieved by our S prime epsilon. So all I know is S prime epsilon is going to be the probability that this belongs to this, given this belongs to this, is at most this. That's all I know. Now comes the reason of setting this epsilon with this latitude value. So this we were calling as latitude. With this epsilon and the fact we saw about how 1 minus p of epsilon is sandwiched between these two numbers, using this side inequality, we can say this. So I'm just plugging in values over here, and plugging in also epsilon value shows us this number is at, like this number is at most 1 by 2 delta. And yeah, so this gives the probability that, okay, this gives half probability. I'll say how. So you know that the probability that I does not belong to S, given it belongs to this, is this value. This is just 1 minus p epsilon root 3 epsilon into capital delta. Now we have like 1 by 2 delta, delta goes out. So this is at most half. So at most half, this shows that as on expectation, the size of this is going to be greater than equal to n times 2. Again, if I say phi prime is phi with one line above, it's just equal to 1 minus phi. So this just follows because we are taking for all vertices. So for each vertex, we know the probability is at most half. So for all vertices in Vi, the summation of probability that I belongs to S prime given I belongs to S epsilon, this is bounded by this number. And okay, it's just by using the before lemma, we can say that. So here we are using the other way inequality. So we use the upper inequality, this one. Now we are using this inequality. By using this fact and just plugging in values, plugging in your epsilon value, you nicely arrive to this number. So thus on expectation, the size of the independent set returned. So this number is not what we need. This number into n by 2 because that's the size of independent set returned. So this number is going to be order of n into delta to the power of minus 1 by 3 ln delta to the power of minus 1 by 2. So this part is just arithmetic, so I don't want to go through that. You take the facts, put in the value of epsilon, you will get this. So this is the size of independent set, which is just, again, we are talking all in expectations. That should be in the back of our head. That is the expected size of our independent set. And from here, directly, you just know that the colors used is going to be ln n by this value over here. Call it Q. This is the number of colors used. So that also proves our main theorem that we wanted. So the exact working, you can see this, I can share the side. It is, except for the fact I mentioned, everything is just arithmetic in between. So yes, thank you so much. And these are the resources that I used primarily. They're also attached right here. And this book in particular is very good for learning STPs and related other techniques in approximation algorithm. So yeah.
Even I am using this book. So like my prof suggested me this book only.
Yeah, it has like everything
Yes,
to do with
yes.
approximation algorithm.